So today I would like to share you some introduction to the GraphQL technology. But before we start, let me give a small introduction of myself. So my name is Oleg Karasik, and I'm indeed a software engineer in coherent solution. So in general, I code in .NET for more than 10 years. And during all this time, I worked on web applications. I even was part of the framework development, shared libraries, utilities, and modern cloud solutions of different scale. So I was lucky to try a lot of stuff. And today I hope I will share some of this experience with you, talking about one particular topic. So our lecture today will consist of 3 small blocks. So the first block will be a brief history of web applications. So we will not dive too deep, but what I will try to do is to highlight the important context for you guys to understand why GraphQL actually appeared on the scene of web development and what problems it actually tried to solve, and in my opinion, solved them successfully. So then we will talk about specifics of GraphQL. So we will dive into definition, talk about schema and how everything works in general. And in the end, we will try to make some sense of what we saw today. So we will see what actually good in GraphQL and when it is profitable to use it, and when it is a vice versa and you should not use it. And of course, in the end, we will look at a bit of statistics because you cannot talk about web technology and do not mention some numbers. Okay, so brief history of web application. So you might wonder how history can help this, because, well, in a major area of software development, every technology tries to present itself as something unique, something isolated, something that actually change the world. However, unfortunately for software engineering, as a very young branch of engineering, the thing goes very fast. So hardware evolves extremely fast. 10 years ago, the personal computers were less powerful than modern phones. The software development as a practice and tools we use also goes very fast. And what is interesting is that our perception as people in society of what application can and should do also evolve at the same time. So all of the things happening simultaneously, and that is why a lot of things you will see, as the problems, they arise only because of that. So I do hope that this short set of slides will help you to bring up this context and to make the problems that GraphQL was designed to solve much more real for you. Okay, so in the very beginning, not in the times of the dinosaurs, but in the very beginning, the web was very simple. So you have a PC, you have some very simple browser in it. You were making GET requests to some servers using HTTP protocol, for example, on a home page. And some distant web servers was taking this statically written HTML page and returning the content to you. Your browser was trying to display something, probably with additional links to additional information. But in a nutshell, that was the web, So one request to the server returned exactly one page. However, serving purely static content wasn't really fun, and it was really hard to maintain it, and it was absolutely non-personal. That is why some smart guys invented a standard and underlying set of technology called CGI extensions, which actually allowed web servers to execute scripts or even executable programs like exe files on Windows in the response to a web request. And as you can see here, as you can see here on this slide, the home is not an HTML anymore, it's ASP, it's a script. And this opened a very interesting door, because now when you have a real program running and processing the request, you can make it personalized. For example, you can display the today's date or today's day or week, and so on. This opened a door for a very, very dynamic pages. So now, because server can actually execute a script, it is become possible to actually receive data from users. As I mentioned in the beginning, everything was evolving at the same time. So alongside these server technologies, browsers also advanced, now supported forms, some built-in buttons, controls like drop-downs, and so on. So users now got an ability to actually pass their data to the web server. And web server started to do some work for the users. So as you can see here, you have a simple form, you enter your name, you click, and some server script maybe saves your data on a disk, or maybe just returns you some personalized page with your name and so on. The possibilities are literally infinite. However, conceptually, it was still one request, one page. And if you posted some form, in the return, you still got a page. And this was really, really a huge problem for a long time. So web was already dynamic. So you can, browse movies and got some list of recent reviews, which wasn't statically coded anywhere. So people were just adding reviews for movies. You can like a movie review, or you can bookmark a movie and it will be saved in your personal file. But the problem is that each of these actions was triggering a full page render. And if you think about it, so the image takes 3 seconds to load. The rating, 4 seconds, list of reviews, 10 seconds, and the first page reload will take 17 seconds, and subsequent reloads will take 14 seconds, because browser was able to cache images at the time. But all of this dynamic content must be recreated, because on the server side, there was no understanding that this is kind of something you can preserve. So this was really hard, and web was really slow. That is why some other group of very smart people invented a so-called Ajax. So they allowed browser to make a dynamic request to a web server without actually rendering the whole page. So now browser stopped to be just something that renders. It started to be something that can actually act and do things. And every page received not only a way to dynamically display some data, but change itself. So the roles of a browser and the server started to change. Now, when you open the home page, for example, you get some initial layout, and then you was able to click some buttons and get this content of this page updated with the dynamic information. Like in this example, when I accidentally had a GET request for Air image ISPX, well, it should be a post, but still you can click on the button and the server will return you a different piece of HTML, which you can replace in some node in a page, and the browser will automatically render a new content without full page reload. This was a very huge advancement, because now pages started to be very dynamic. You can have a grid with a pagination, and it will not reload the full page all the time. You can make any kind of actions. And the important moment here is that the communication pattern between client and the server changes drastically, because now one page doesn't mean one request, and request doesn't mean you're getting a full page in response. So servers started to feed not only full pages like on initial reload, they also started to support partial results. So the logic of one page now can be spread across multiple web server endpoints. So in time, this evolved even further. So advancement in the JavaScript, more powerful PCs and browsers, more API in the browsers, allowed developers to actually create a full applications inside the browser. So now, and this is true for right now, for today, for web, many browsers actually act as operating systems for the web applications. If you think about it, when you open some site, they do load some content, and then everything is happening in the browser. The forms are dynamically printed. The pages are not really pages. You are just clicking on some navigational instruments like buttons or links. But in reality, you are not making additional requests to the server. This navigation is virtual. The browser emulates this movement across the pages. It can change the URL and so on. But in a nutshell, inside it, there is a web framework engine which actually dynamically renders the content of the page, makes additional requests to a server to get the data, and it actually transforms the roles of a browser and a web server, like browser became a host, like an operating system for applications, and a web server evolved to a simple data backend. So there was no instances when web server will return your HTML except the first request to the index HTML. And technically speaking, this is an architecture of a majority of modern web apps. So a huge single page application on the front end and a data backend. So unfortunately, these advancements make everything very, very complex. So because browser can now execute a fully fledged applications, it somehow immediately pops up that requirements for this application started to be very close to what we have from desktop applications. So they should have a smooth animation, they should be very fast, they should display data in a way it is convenient for a user, because in the early days of web, most of information was displayed in a way convenient to render it, because everything was very slow. But now you have an app which dynamically renders in a matter of microseconds in your browser. So why not to create these cool pages? On one, you have a few complex filtering. In another page, you have details. And this led to the situation where actually one page might display data from a completely different data entities. So as you can see on this slide, on the first page, we have a filter with a department name, then a filter with a country name. Then we have a list of users, and each of these users displays username, job title, and again, country name of the country they are in. On the second page, we see a list of departments, and we display department name, number of people, and then we are displaying a department manager name. There is also an address in the bottom line. So this page looks organic, so it's nothing surprising here, but from the point of data layout, they're quite complex. And this created a very significant challenge for the server side, because now when developers on the server had to design the API, they were forced to fight for three absolutely contradictory quality. So first of all, it's reusability. API must be reusable, because otherwise any change to the UI, any new page, any new control will actually force you to develop more and more API. And from the software development perspective, this is very costly and this is very inefficient, because all UI features will always wait for backend to be done first. The second is transparency. If you create hundreds and hundreds of endpoints, and these endpoints will be very cryptic, they will return a completely different set of parameters and so on. New developers that will come to your project, they will not be able to join fast, to understand it. And it goes both for front-end developers who will actually consume your API and the back-end developers, because large API surface really hard to support. Just imagine you're changing some database entities, and now you need to change dozens of API endpoints where these database entities were used. So it is really hard here. And the last but not least point is effectiveness. So the API endpoints actually need to strive to return as much of useful data as possible. So it is bad if you need only a country name, but you will return country, all business units from this country, I don't know, all the names of the managers in these business units, while you actually, all you need is just a name of the country. So returning this extra data is not only bad for network latencies, but it's also bad because it forces the server to do more work, to spend more CPU cycles actually collecting and processing this data. So this struggle leads to emergence of two, well, let's be honest, not two, a lot of API design styles. Today, I will try to demonstrate you the two that I saw the most. And the first one is so-called RESTful API design. So this API design is based on a very famous REST principles. So, and which actually, if you never read Roy Fielding's dissertation, his thesis, I really advise you to do so, because they really explain how modern web works, because his theses were based on how HTTP protocol actually makes the web extensible. But long story short, the RESTful API design proposes to treat all of the data as a resources. So you can see here, like user is a resource, department, business unit, and country. And if you look at this API endpoints, it is very clear what they do. So if you get API/departments, you get all departments. If you get this ID in the end, you get a particular department. And when you get a department, you get information about this department. So RESTful API is a very good example of high reusability and high transparency in the API design. So these endpoints really reusable. You can create many pages based on them, and you will not need to do any API change. And they are already very transparent. However, the downside of RESTful approach is that it actually has a very low efficiency. So if you take a look at these fields, some of them are marked in red. So across these two pages, these fields weren't used. And if you look at the green fields, these fields are something that need to be resolved with an additional API call. So actually, to get a department and its name for the user, we actually need to make a call to the department endpoint. This created two problems: over provisioning, so we return more data that we actually need to consume, and multiple requests to actually collect all the data in a single piece. That is why there was a second approach. It has no official name, but I saw it many times of the project. In the scope of this lecture, I will call it a granular API. So this approach was very on the opposite side of the spectrum to REST. So the idea was to create endpoints which will actually return what UI needs, plain and simple. And of course, the major advantage of this approach is that it's very highly efficient. So as you can see here, if you do not take in account mistakes that I colored in green, the country here, like it looks like it should be resolved, but it's not, it has a different meaning. So except this, you can see that there is no data that is unusable. All of the data in these endpoints actually gets used on all of these pages. So this is very efficient. However, if you try to imagine a third page, you will quickly notice that these endpoints aren't really reusable. You can try to reuse it, but it will feel really artificial. And of course, you will immediately hit the problems which RESTful API hits. You will either over-provision or you will need to resolve something. But the bigger problem is not reusability here. The bigger problem here is that these endpoints are not transparent. So the country field, which I marked in green, actually indicates that just looking at this request, it is really hard to say what this country means. Is this a country where user is from? or it is a country of a business unit. And if you see on the endpoints names, like API search departments, API search users, they do indeed look cryptic. And, in scope of this presentation, you might think that, okay, Oleg, you just created this issue, to emphasize your point. And partially this is true, but to be honest with you, you can even, make a screenshot of what you see on the screen and then sit down and try to come with the better names. And you will see that is not easy. And here we have only 1, 2, 3, 4, 5, 6 endpoints. And imagine you have 100 endpoints. Can you imagine what clumsy names it will be full of? This will be a big problem because people will completely not understand what they need to use. So just to demonstrate you how it works, so here is the page number 1 gets resolved by a RESTful API. So here we need to have at least 6 requests. I'm saying at least because in this example, I believe that what we do is that we retrieve all departments, then we retrieve all business units, then we retrieve all countries, then we get all the users, and in memory, inside our browser application, we actually match all of the stuff, like a SQL joining them by IDs. This will take 6 requests. If for a mere moment you will think about resolving all of this individually, the number of requests will start to spike dramatically. So we can easily hit more than 25 requests just for this page if we will try to resolve all of the stuff individually. And on the right, you can see that from the granular API standpoint, it is much better. You need to have exactly 3 requests. This might seem like a very huge benefit because, well, it's at least twice as better as REST. But what I wanted you to think is that you still need to have at least 3 requests to render a simplest page ever. This page actually so simple that I would call it a dialog more than a page. And you still need to have 3 requests, even if you design your API more or less granularly to be very focused on control level. For the second page, for granular API is much better. The search department endpoint actually fills all the data. And for REST, it is a bit better, but we still need to have at least 4 requests to actually get all of the data. So you can see that in some cases, approach with a granular API can be much better than REST API in terms of number of requests. But in general, you still see that the problem do not go anywhere. You're still making many requests. And if you will scale this up, saying, I have dozens of pages, there will be much more pages which need 10 or 15 requests than pages that will need only 1. So this historical context brings 3 major problems that we have right now. And this is true even for modern web applications. This didn't go anywhere. This is something that we can encounter right now. So the first one is over provisioning. As I mentioned, the more reusable API you create, the more extra data you return. And this is bad. It wastes bandwidth. It actually wastes CPU cycle. And in times of a cloud, when everything is hosted in cloud, and cloud bills us for the seconds, on a second basis, every wasted cycle is directly transformed to money. So over provisioning increases the cost of your application hosting. Actually, it makes it worse for user because if you have a bad network connection, downloading 5 megabytes of data instead of 1 megabyte is a huge deal. Second problem is too many requests. So to keep API surface somehow reusable, you need to have more or less generic API, like RESTful one. Then you will need to fetch, full page of your data, you will need to make many requests. Every request has a latency. Every request adds additional load time to your server. And the worst thing is that some of the requests cannot be executed in parallel at all. So for example, if we will need to get a business unit of a department, we first need to get a department. We will find an ID of business user and make a request to business user. So this too many request problem actually results in a situation when you open a page in the browser and you can see like elements popping up, with some delay all over the page. And sometimes to get a full page load, you're waiting still this same 10 seconds, and it was in the times when the whole page was rendered on the server. So this is a very huge problem. And the third one is ever-changing API. So because API designers still need to struggle between reusability and efficiency, in a lot of cases, they try to pursue both, and this leads to creation of a semi-efficient, semi-reusable endpoints, so they are not really reusable, and you need more of them, but they are not super efficient, and you are still over-provisioning. And this actually leads that almost any noticeable change to UI results in the API endpoint changes. And as I said in the beginning, it is bad because in this case, you always need backend developers to be involved. So you cannot just separate front-end work from the backend work. So it will be unfair to say that no one tried to solve these problems. So first of all, to reduce a pressure in the network, developers started to compress everything. So gzip compression is natively supported in the browsers. A lot of modern frameworks natively can gzip, so actually compress your responses. And because a lot of communications happen in a text format like JSON, it works very well. So compression ratio is more than 2 and 3 times, so you significantly reduces the amount of data transfer between pages, but it's kind of a patching to a problem, so it's not a real solution. The second thing is caching. So of course you can cache stuff because on browser, like an operating system, inside the browser in JavaScript, you can allocate a lot of objects, you can save responses, and you can reuse the data across multiple pages. And actually modern frameworks like React and Angular encourage you to do so. So you kind of request something in a parent component, and then you spread it down the tree of components to lower level components. So you actually making sure that you request data only once, and all of the UI tries to consume this data without making a separate request. It also made the situation better, but actually the problem is still not solved. So some of the problems with that loading time was trying to be solved by using prefetching and late loading. So the first one actually tries to prefetch the useful data while you're rendering a home page. So you're accessing a home page, and at the same time, we kind of, users usually open this statistics page. So we will load all the data for statistics page. So for the moment, when user clicks on it, it will kind of rendered magically and immediately. The late loading is another technique that actually saves network bandwidth. Especially it is good for low quality connections, and actually saves CPU cycles. So for example, if we have some blocks of a page which users do not usually scroll, then we didn't need to load it at the time, right away. And the last thing is backend for front end. This was a very interesting architecture approach. It is still very popular, and well, I saw it many times in my experience because it works pretty well. So the idea here is that for every front end, and by front end, usually there is a notion of application, like for web app, for mobile app, for desktop app, or maybe even for different flavors of web app, you're creating some sort of a small granular API surface, which works very efficient. But this granular API surface actually underneath utilize the internal RESTful API. So you have a layer of RESTful API, and in front of it, you have a layer of backends for front ends. And then you have a clients. So clients efficiently communicate with backend for frontends, and backend for frontends communicate with the RESTful API. This kind of allows to create a very fast and very scalable architecture, because you have some internal team working on RESTful API, and then you have teams that can quickly and sometimes even dirty extend this granular API and adapt it in a way it is useful for their application. So this is also a very good thing. In combination, all of this stuff makes the web much better. But still the problems, conceptually, these problems weren't solved. So this is where GraphQL comes in, actually. So these three problems, over provisioning, changing the API, making too many requests, GraphQL was designed to actually nail them down. Let's try to understand how it can do so. So classically, when you start to get to know something really, really new, it is good to start with a definition. And this is what we will do today also. So from the official page of the GraphQL.com, GraphQL is defined as a query language for APIs and the runtime for fulfilling these queries with your existing data. I would be honest with you, it is not really easy to read it from the first time. I'm kind of feeling a need to put a comma somewhere. But to make it easier, we can try to highlight the key elements of this definition, like that. So the first key element is that GraphQL is a query language. So there will be some abstract language to describe the query. Then it is API, which seems pretty obvious, so we still need to make requests somewhere. Then there is something called the runtime. It is not really clear what it is from the definition, but it is somehow will probably do the data. And if we will try to connect all of this stuff together, we will receive a chain which looks something like that. So we describe our query using a query language. Then we may take this query and send it to the API. So API accepts our request, forward leads to the runtime. Runtime performs some sort of a processing of this request. And using our existing data, it somehow fulfills it. So technically speaking, it returns the data requested by the query. If we try to shred some elements that are not really critical here, the picture will be much more simpler. So we have a query language, we pass a query to runtime and get the data in the return. Logically, sounds pretty simple. So let's see how it works. So we will start from discussing what the query is. So in GraphQL, everything in a query starts with a so-called root query operation. So you can see here on the screen, we have kind of two separate query windows in our imaginary development environment. So the one starts from the word query, and the second starts from the word mutation. So the last one says that we are going to fetch the data, and the right one said that we want to change our data. Both of these things are called queries. So query sometimes can be confusing, but think of it in that way that this is a query, and query and mutations are operations. So all queries are described in a JSON-like syntax format. You will see it in a future slide that it is very convenient. And the content of this query operations is actually defined by a so-called query schema. So just for you to be prepared, so GraphQL actually is a typed query language. So query schema actually describes types, like that one. So the basic element of the query schema is a type, which is obvious. So it is declared using a keyword type. It can have a name, like in our case, the name is a magic effect. It can have a fields. You can see fields are marked in blue and their types are in green. So here in this particular type, we have a field name with a string type, field probability with a float type, and field power of an integer type. And all of these fields are combined in the magic effect type. Besides types, GraphQL supports enums. And if you ever saw any kind of programming language, probably enum is the well-spread notion of how you can define some things that can only enumerate, but you cannot change. So definition starts with the keyword enum, and in the body of it, you're just specifying the values. In addition to types and enums, GraphQL schema supports interfaces. And because there are interfaces, there are notion of inheritance, of course. So interfaces are declared very similarly to types. Probably the only exception here is that interface is actually defined with the keyword interface. I also want you to point here that you can see we are using our enum, like a weapon grade, and now we have defined it on the previous slide, to define a grade field. So actually, the types you used you define in the schema, they are not obligated to use only these basic scalar types. So they can use types and types and types. So as I already mentioned, there are built-in so-called scalar types. These scalar types actually power up all of the GraphQL schema. So when you start to develop your types, you kind of need to add fields, and these fields need to be of some types. And in GraphQL, there are 5 built-in types supported. So the first one is integer. So int represents a 32-bit single integer. Boolean, of course, represents only a true and a false values. String represents a sequence of Unicode characters. Float is a double precision floating point value. And ID is a unique identifier. So while it has to be unique, identifier, it is not a number. It has to be represented as string. But the interesting thing here is that this ID is not obligated to be human-friendly in any way. So it can be just a gibberish. The only requirement for it is to be actually unique. So having all of this, we can start combining our stuff. So on this slide, you can see that now we are defining a type called magic weapon. So again, we use a type definition. We inherit the iWeapon interface. You can see that fields, damage, range, and grades are replicated from the base interface. And we add a new type called a new field, called effect of a magic effect type that we actually define it in the very beginning of our query scheme. So this is a good example of how powerful GraphQL schema can be, and you can imagine that you can go on and go on defining more and more and more stuff on that, and actually create a real type system for you. So besides defining types, GraphQL schema also supports a notion for fields. So actually, there is much more than I am describing you here, but we will focus only on these two because, in my opinion, this is a major things. So the first one is an exclamation mark, which you can put after the field definition. And it will say that this field is required, so it cannot be null. And the second notion is that when you put a type in square brackets, it will actually indicate that this field is a list of type. I don't know why they called it list, because in every other software development area it's called array, but technically this is array. So you cannot dynamically add items or remove items, so there is no pure list behavior, but it is called list for some reason. Okay, so now we defined a lot of types. How we can make a query? To make a query, we actually need to define one more type. This is fun because you kind of need to define a type to use your types. So the difference between types that we previously defined and these types is that it has a reserved type name called query. And this type query will be automatically mapped to the query root operation. So every time when we will write query, the GraphQL will think about this particular type. And as you see inside this type, we expose only a single field called player of the player type we have defined on the previous slide. Okay, let's use our imaginary IDE to actually make a GraphQL request. So on the left, you can see the query. I didn't want to start with a very simple queries, like in the tutorials when you request only one field, and then lecturer said, well, that's it, you now know GraphQL. So I was explicitly wanted to avoid this. That is why we will make a pretty complex query right ahead. So we will request information about player, we will request information about its main hand weapon, and what weapons it has in inventory. So as you can see, the left and right side looks very, very similar. And this is not a coincidence. So on the left side, we describe a query, and as I mentioned, it is a JSON-like. So you put fields, you open a curly bracket to define like an object scope, and you put the inner fields and so on. In that way, you're actually describing what exact data you want to receive. And in the response, you will receive a JSON, a real JSON object, which will have a root element data. And the structure of this object will mimic your query, which makes it really, and I would even say super convenient to consume because you actually get exactly what you requested. The interesting thing here is that in an inventory field, we actually received an array in the response because our player has two weapons. If you look closer, you might notice that main hand and inventory, if you can recall, they both are of iWeapon type. So we define the same fields for them to retrieve them. So in this particular example, iWeapon has 3 fields and we request 2 fields. So it's not kind of a problem. But if you imagine a very huge, entity with dozens of fields, replicating this entity on all levels will be very cumbersome, and it will make query really large and really hard to consume. Fortunately for us, GraphQL got this handled. So GraphQL supports a so-called notion of fragments. So fragment is a piece of reusable query. So you defined fragment as part of your query. So what you do is that you use a keyword fragment. You give this fragment a name. In our case, it's named a weapon. Then you set what type, what fragment of what type this represents. So you have, in our case, this is iWeapon. And we say that we want in this fragment to include grade and damage. Then in our main hand and inventory fields, in our main query, we use a spread operator with the name of the weapon to actually include our fragment. As you can see, query immediately started to be much smaller. And believe me, if you will write a lot of this query, you can write multiple fragments and your queries will be very small, very concise, and very extensible, because if one day we will decide that we need not only grade and damage, but something else, we can just include it in the fragment and all of the queries will immediately get it in the responses. So one interesting thing that fragments actually can be used for is to resolve fields of a particular type. So as I mentioned, our main hand and inventory, they are of interface type, so for iWeapon type. And on the magic weapon, we actually have an effect field. Previously, we were not able to retrieve it because you cannot specify fields that are not defined by type. The GraphQL validation will not allow you to do so. And because iWeapon do not have effect field, it was not possible for us to specify it. However, we can define a so-called inline fragment. So you can define inline fragments in both in the main query or inside the fragment using the same syntax. So you start with a spread operator, then you specify a concrete type, and then in the curly brackets, you specify a field you want to retrieve from this type. And the fun thing here is that these fields will only be returned in the final JSON if actually the field on the server has this type. So if your field actually matches. And you can see that in our example, only main hand weapon actually was a magic weapon. That is why we got an effect with some name called, I don't know what it is, but it is some magic effect. And for inventory, we didn't get any additional fields here. Immediately, what the question arises is that, hey, how can I distinguish when I consume the result between, main hands, that it is magic weapon, and inventory weapons? GraphQL get this handle for us. So this is a so-called meta field. So you can define a meta field type name, and when you will get a response in this meta field, you will actually have a name of the type from GraphQL schema. So in our case, you can see that I removed all of the types to make the screen fit all of the response, and I added type name. And immediately on the main hand, we received the magic weapon, and on inventory, we received just a weapon. We never defined weapon type, I imagine it, but this is how it will look like. So on a client, if you need to consume some specific and make some dynamic behavior based on what types are returned, you can use this inline fragment, retrieve additional types, use a meta field, and actually parse your data on the UI pretty easily. However, all of this seems very exciting. You can request only fields you need. You can request, like a dynamic polymorphic fields. You can do a lot of stuff, but the simple question is how we can get another player. Currently, we were getting this John player all the time, but what if I want to get another player? How can I do so? Well, GraphQL knows how to do it. So in the terms of a GraphQL, what we need to do is that we need to extend our query schema. And by the way, it's not specific only to a query type. So you can add these so-called arguments on any field of any type. So any field can have 0 or many arguments. We are doing this on the query because we are trying to find a new player. That is why we're kind of making this change on the root level type, but in general, you can do it on any type. So we will define an argument. So we will have an argument name ID, and we will say that it has a type ID, and this type is not nullable. So now every time when we will make a request for a player, we actually will need to specify the ID argument. So in our imaginary IDE, all we need to do is that open parentheses and actually put ID argument inside it, because as you remember, IDs are represented as strings. So we put a string 2, we make a request, and voila, we get a different player named Clark. Pretty easy. So what if we want to retrieve 2 players? As you remember from the very beginning, the data in response always mimics what you have in the request. And if we have 2 players, then JSON doesn't support, duplicate keys. So these 2 players will not fit. So it will not work. So for this particular situation, GraphQL supports a so-called aliasing. So the idea here is that inside the query, you give your field a different name. So in our case, we have a left and a right name. Maybe we want to compare this player. So we have a left player to compare and the right player to compare. So we give these new names, and then we proceed as usual. So we specify a player field, we put ID 1, then we specify a player field and put ID 2, we put fields we want to retrieve, and in response, we will get absolutely the same structure. And by the way, there should be a comma after the left in the response. So actually, for some reason, my ID returned invalid JSON for us. I will definitely fix it later. So we will get a response that completely mimics the structure again. And actually, if you think of it, it opens really almost infinite possibilities. The only problem I can see right now, the only thing I don't understand how we can do right now is how we can get rid of these hard-coded IDs. So besides this, GraphQL actually does everything we can even imagine. So, and this also got covered because GraphQL support a notion of variables. So what you can do, this time you do not need to extend the schema. So what you can do is that you can add a variable on the top of a query operation. So on the top of a root operation, we are adding a variable name ID with type ID. Then we kind of pass this variable in argument, and in a separate JSON, we define this variable. So here I need to say a few words how GraphQL queries are actually sent to the server. So actually they're sent as a JSON payload usually, and the query is sent in a query field. So we have a query field and a string, which includes all the query. And variables are actually sent in a separate variable field. So you will have this JSON stringified in a string. So what you will send to the server is an object with a query and variables fields, which both will be strings. So this actually allows you to define queries and then reuse these queries dynamically with different variables, which is kind of really cool. And as you see, a response is unaffected. It is completely the same as it was previously. So kind of summing up all of what I said, you can immediately see that GraphQL nails everything. You have reusability because you can use the same GraphQL queries, for many pages. The only reason for extend your GraphQL query schema will be if you need to define a new type or add a new field. So only if you actually need to do something to extend the domain of your application. For all other cases, you can just specify fields you need and get everything immediately. And as you saw, it is very powerful. You can get multiple players, you can get arrays and so on. It kind of definitely nails up the reusability. And the same goes for transparency. The query schema, the query language is very easy to read. The data it returns mimics the query structure and is a pure JSON, which is kind of user-friendly. Well, not user-friendly, let's call it developer-friendly. So, and actually you have a schema which explicitly defines the type. So you can say, okay, the player ID, what type of a player ID, what should I send? You can open the schema and you immediately see that it is of ID type, and therefore you need to send a string. And of course, it's very efficient. So it's kind of out of question. You receive only fields you actually requested. So absolutely no waste. However, when I first meet GraphQL, and probably you guys have the same question here, is that how this left side actually gets to the right side. How we turn this query into this response. How writing something in a schema and actually putting it in the parentheses makes filtering work. So how just changing some text files actually made this happen. How we actually influence what was fetched from the server. And these are really great questions because they arise for the reason. Everything that we have discussed by far, absolutely everything, was about query language. And the query language, as I said in the very beginning, is a way to describe what you want to get. So that is why we changed the schema to add an argument, and that is why we changed the query to put this argument, because we changed what we want to get. So we changed our intention. But all the hard work is actually done here inside the runtime. So query language is very expressive, but without a real runtime support, nothing will be returned. That is why it is impossible to talk about GraphQL only in terms of how cool query language is and how amazing you can request everything and so on. you always need to know that behind the scenes there is a runtime. And what runtime actually does is that it bridges these clients which write queries and data which is stored in probably some database or data source together to create this response. Just to put it plain straight, runtime is not a magic. Usually it is some sort of reusable library. Nowadays, there are few reusable libraries for different languages which implement the GraphQL specification. So these runtime libraries are able to parse the query and execute it, and then return the result. So it is just a library. And in terms of modern web application development, we can even say it is a package that you include in your application. And what this package does is that first of all, it knows how to parse the query, and it knows it because you actually have a query schema. So all your GraphQL journey as a developer starts from the fact that you are defining a schema. This schema will give runtime all of the information it needs to parse and actually validate the input query. Because here we have a player with a required ID. So if you do not specify ID in a query, it will not make sense. And runtime need to return an error, validation error to you. And to know that, runtime need to be able to access schema. However, besides performing a pure parsing validation, runtime also knows how to map query to application code. And runtime knows this because when you're defining a schema, usually it happens somewhere on application start type, and depending on the programming language you are using, it can be done, absolutely differently. But in a nutshell, it will be the same action. You're defining a schema, and then you say, okay, runtime. So if someone will need to work with a query, you need to go to this query resolvers class, and this is where you will find methods, application functions that you need to call to resolve fields. And for the player field, you will need to call this getPlayer. And for player's ID, you will need to go to the separate class and call a getID. So there is absolutely no magic. It is just a very complicated mapping, which gives this runtime a possibility to parse the query and say, okay, I need to call this, and this methods. And all of these functions, in terms of GraphQL terminology, they're called resolvers. And of course, the last thing is that runtime knows how to execute application code to actually fetch the data. So when it receives a query, it will analyze it and calls required methods in a required time. So it will be very well orchestrated. So let's see an example. So let's run our imaginary IDE and see the runtime trace to understand how runtimes actually parses and processes the query. So we can see we have the same simple query and runtime accepting the query. Now it found the root operation query. It resolved the operation type to query. So this is the type from our schema. Then it resolved the type to type resolvers called query resolvers. So these resolvers are put in an execution context. So runtime knows that I need to use something from query resolvers right now. So it scans for the fields and finds the player field. So the player field is identified to have an argument named ID with the value 2. So the field is resolved to type player. So as you can imagine, this is validated right now. And because player actually cannot, and the query has accepted ID, so we need to resolve resolvers for a player type to be prepared for future work. And then we actually invoke query resolvers to get a player with the ID number 2. So when we are done with that, we are updating our context. And in this context, we now have player resolvers. You can see they're on the first place right now, not the query resolvers, because this is what we will use right now. And in a context, we have an object of a player type with the name ID. So now we keep scanning for the field. And we find the ID field. The type of the field is resolved to be ID. This is a scalar type, so no additional custom resolvers are needed. So all we need to do is that to invoke player resolvers get ID. And here is a very interesting thing. We are passing our player as a context here. So when you do all of this mapping on the application startup, you actually write some code that will show how the context is propagated to your methods. So in our case, we know that we need to receive a player. So player resolvers get ID methods actually receives a player object. So, and when the method is executed, we are getting the player ID in the output. So as you can see, now our context contains resolvers, context, and output. We keep scanning for the fields, but unfortunately there are no more fields. So no fields found. We are returning for processing the player field on a level up. And now again, you can see the context is clear, so we do not need a player anymore. We throw it away. We do not need player resolvers. We throw them away. So now we have an output and query resolvers type. So we are keep scanning the query. No fields found. We are getting back from the query operation. So we throw away the resolvers again. And here we have an output. So the output right now is just a player ID equals to 2. So what runtimes need to do is that it needs to prepare the query result, return the result to the client, and the operation is completed. So the very interesting thing from all of this process is that it is clear that what runtime does is just orchestration. So it parses the query, it understands what needs to be done, and then it orchestrates the whole execution. And what is very important here is that runtime absolutely do not understand what happens inside the resolvers. Like, absolutely no idea. All runtime knows is that I need to call this method at this particular point of time. And this creates a very interesting side on the server, because all application logic to retrieve or make anything with the data starts to be concentrated in these tiny resolvers. So we can assume the context in the resolver, and we need to write application logic, and that's it. And this is very important because it opens the door for very interesting possibilities by the runtime. So the first one is that this query, where we want to retrieve two players to compare them, actually can be executed in parallel. Because all runtime needs to do is to call resolvers, and we, by the definition, we know that querying stuff in parallel is usually safe. So runtime can assume, okay, I have two player fields, I will resolve them in parallel. So runtime doesn't need to know the specifics of the resolvers implementation. It doesn't even know how deep resolvers will go. Runtime just knows that I can start resolving stuff in parallel because all of the logics between resolvers. And from the server side, you do not need to write even a bit of code to support this parallelism. It is supported automatically for you. All you need to do is to actually describe how you will resolve all fields, one by one. And this orchestration and abstraction of what the code does actually opens even more possibilities, because resolvers actually can fetch the data from absolutely different sources. So, for example, a player resolver can fetch the data from relational database. The ID resolver of player can obviously take the value from a field. The same goes for the name resolver. And for example, inventory resolver, by some unknown historical reasons, might fetch the data from a very slow hard drive file. No one knows why it might be needed, but technically it is possible. But the great thing here is that because runtime goes field by field and invokes resolvers field by field, if you do not specify the field in the query, resolver is never called. So in our case, we will never call this very slow, clumsy inverter resolver at all. We will call only fast player ID and name. But this is not the most amazing thing here. The most amazing thing here is that these abstractions actually allows you to implement changes to the data using absolutely the same infrastructure. So in the query side, mutation reuse absolutely the same query syntax. The only difference is that root operation is called mutation, not a query. So you can use everything. You can use fragments if you need so. You can define multiple fields in a row, and all of this will be absolutely the same as for query. And in the query schema side, it is also completely reusable. As you can see, the mutation for a player to create a new player actually looks absolutely the same, well, except we are accepting the name instead of ID as we did for the query. And in the response, this is the very fun part. You will receive response in a very same fashion as you actually made the query, because the ID field we do specify in a mutation will actually say to GraphQL that after you execute all of the fields, you need to kind of execute ID field. And because we have a resolver for ID field, which actually reads it, it actually will read it. So all we need to do to support mutations is it's somewhere deep in the server defined a separate resolver for mutation type that will create a new player and return it. So it will look absolutely the same like query, but instead of actually getting the player from the data, we will create it and return the object back to the pipeline. And GraphQL will reuse all the full power of its infrastructure again and get us a beautiful response, at the same time creating a new entity. And the thing here is that you can do even such complex query and not be afraid, because runtime can actually distinguish root operations, so you reuse everything. But from the runtime, mutation and queries are a bit different. And if you write this kind of query to create two players, runtime will execute them sequentially. So runtime will execute the creation of a player John first. When it is completely done with that, it will collect all of the fields and so on. Then it will execute the player Katie, and again repeat all of the retrieval of the fields here. So what I can say is that this architecture of runtime being an orchestrator between client request, a query, and actually application codes allows a complete reuse. So we actually have absolutely the same instruments on both client and the server to define both data retrieval and data manipulation. And actually, this is mind-blowing. So when you try to realize how everything this was tied together in a single node is really, really very cool. And this technical brilliance is not a luck or coincidence. It is actually a result of a very hard work. So for Facebook, it took 3 years to just develop and release a draft specification and a small reference implementation of a GraphQL to open source. And only in 2018, 3 years later, the GraphQL schema language that we used here to define our types officially became part of the GraphQL specification. And if you're interested to read the specifications, you can go to graphql.com. They have a very great tutorials and very in-depth explanations, because I will be honest with you, here I showed you only a tip of the iceberg. Because we have a limited times, I had to remove a lot of stuff, from the GraphQL, so I didn't demonstrate you, but it is much more powerful that you can see even from what I have demonstrated. Okay, let's try to wrap up slightly what we have saw today. So first of all, GraphQL is a rich and highly extendable query language. It allows clients to retrieve all data they need in a single request, essentially nailing up the over-provisioning and too many requests problems. Secondly, is that the GraphQL queries are executed by runtime. So runtime is a library or a package, if you can say so, that can make sense of query schema and can map it to some application functions that it will need to be called to actually get the data or perform data manipulations. And the best thing is that GraphQL queries use the same query language and the same query schema, and what is very important, the same types. So if we need to define a query for player and mutation for player, we can reuse the same player type, actually, to describe query, which are fetch data, and mutations, which are change data operations, which makes it really cool because all language features are available for both use cases. And last 2 points is that when runtime executes the query, root operation, it can take an advantage of the knowledge that queries can be executed in parallel and actually execute a lot of resolvers. And most runtimes I saw do implement this technique. So all resolvers on the same level are executed in parallel. So this actually makes a lot of queries, even big queries, execute really fast. And the second thing is that mutations operations are automatically synchronized and executed from top to bottom. So they're executed in the order you actually describe them, which makes it really easy and convenient for developers to actually create multiple objects or perform multiple changes to multiple different objects in the same query, because you always know an order of the operations. So we are almost out of time, and I would like to think about a few cases where GraphQL actually can be great, because I don't want you to have false thinking that GraphQL is some magic stuff, and from now till the end of your days, you need to use it in every application you write. GraphQL definitely solves a lot of problems, but it is not a silver bullet. So you need to use GraphQL when communication patterns between client and server constantly suffer from over-provisioning. Believe me, if you return a single extra field, this is not a use case for GraphQL. However, if calculation of these fields will require 10 seconds, then probably it might be. So here you need to consider amount of data you return for nothing and the cost of actually returning this data. If you just return a few extra fields from an entity which you fully retrieve from the database, well, this is not the case for it. Secondly, is GraphQL really shines when you need to do a really, really great number of requests to retrieve the data. So if your application displays on a single page data from various sources or multiple instances of the same data, but with different IDs and so on, like an example, when we wanted to compare two players, and in typical REST API, you will need to make literally 2 requests for 2 players with different IDs. So this is where GraphQL can be of very high use, because it will pack all of this query in a single query, and you will greatly reduce network latency because you will need to have only 1 request, and you will greatly simplify the communication pattern. And because you can request only fields you need, you can literally write, and this is something that is quite commonly used in practice, you can write 1 GraphQL request for a page. or for a huge component, for example. And of course, GraphQL is great when you need to build an API that can be effectively reused across multiple clients with minimal or no support. So if you expose enough types with enough of type arguments, field arguments, and so on, you can actually create the API surface that can be used by UI to create different pages. It can be used by a mobile team to create an application. And this will be done literally without contacting the backend at all. And what is really fun is that you can expose this API to your clients, for example, selling it for some money, and your clients will be able to build rich applications without coming to you all the time and say, hey, we need more money point here, and this part works really slow, and so on. So this is really good. However, as I said, GraphQL is not as a silver bullet. So if by some reason you cannot use existing libraries which implements runtimes, believe me, GraphQL is not your options. Because just looking at this small part of a query schema that I described to you, and all of the stuff the runtime need to do to map schema to types and then parse a query, this is a project that you can literally dedicate a part of your lifetime. So that is why there are not hundreds and thousands of GraphQL runtimes. Usually there is one runtime per language, and it is open sourced, and people in community try to support and extend it because it's very complex. It has a lot of performance challenges that need to be solved. It needs to be adapted to the language specifics. It needs to be constantly supported. So this is not a weekend project. That is why if by some reason you can't use it, then GraphQL is not an option for you. And secondly, there is no need to use GraphQL if your API surface is small and it doesn't have a deep nested relationships. So if your API surface is really simple, the RESTful API design is the best you can take for now. So I would even say that majority of the applications which are not feature rich, which are not exposed to billions of clients, can live with a RESTful API design and do not suffer from any issues because everything will work pretty smooth. The caching is very powerful right now. Browsers are fast, servers are fast, and so on. And GraphQL actually comes with an additional cost because you need to parse the query, you need to process, keep of this in memory state, and so on. And it all wastes memory and CPU cycles. And also, to be honest with you, to develop application logic in scope of resolvers, it also requires some effort from developers. It is not hard, I did it myself, but you still need to get used to it comparing to the convenient way of defining endpoints and endpoint logic. Okay, just to finalize everything I said, here is the small statistics I gathered probably yesterday or a few days before today. So what I did is that I opened the development tools and I just hit a homepage of BBC, LinkedIn, Microsoft, Auth0, Medium, and IMBD. So the results are pretty interesting. Of course, just keep in mind, not all of these requests are actually data requests. Some of them are post requests, some of them are analytics requests, and so on. But still, a lot of these requests are for data. And I didn't took into account any images, so I got filter all of the requests only but what is made explicitly by Ajax. So as you can see, BBC have 45 requests to render the homepage. LinkedIn has 152. It's amazing that in the first moment that you see a content and the page looks complete, it still pops up lots of requests to prefetch a bunch of data for you to be able to actually use this page, without feeling any lags or delays. So Microsoft homepage is very simple. but it still consumes 32 requests. And our 0 has also a very simple page, and it takes 26 requests. So when you open a medium.com, you can see it has 4 GraphQL requests. Most probably there are huge components, very isolated components which have their own GraphQL queries to supply their needs. And in total, they have 18 requests, and most of these requests actually for analytics. So I didn't do a very deep analysis in this, but for Medium, it was very simple. So 9 of these requests were actually analytical requests. But my favorite example here is IMDb. So if you open IMDb homepage, you are immediately presented with the pictures, with information about movies, with some news. So it's pretty data rich, but actually it has only 8 requests, so something like that. 8 requests. And 5 of these requests are GraphQL requests. So it is very huge comparing to all of these pages which do not use GraphQL. And this is can be an illustrative example of how you can really see it in action. And you can also measure how fast IMDb loads. Actually, it is pretty fast. So you do not even feel the lags on it. That was all from me. Thank you very much for listening to me. Maybe you have any questions. We still have 5 minutes, if I'm not mistaken.
Okay, do we have some questions from students? Okay, so if there's no question, I would like to ask first thing for the lecture. I like that it was very structured. So the idea, what problems are solved, how they are solved, and when to use it and when not to use it. So
Thank you.
fantastic. So for the students, I will not ask to write to you schema of the query, but to know these things you need for the test. You need to know all those things. When to use and not to use, what's the idea, what problems are solved. And also I want to ask, in your company, how many applications use GraphQL and the other side REST API?
Well, the majority is for REST API, of course. So this is a very popular, and as I said, it fits a lot of applications. But we have a few which use GraphQL, and the one application I actually work on, it uses GraphQL, but we do not use mutations. We use only query parts. So we have a combination of RESTful API and GraphQL. So we use post and points to change and create the data, and we use GraphQL endpoints to query the data. And it is kind of very convenient because we have a lot of pages which need to display the same entities but with a different context. And that is why GraphQL querying query works for us, because we retrieve only the pieces we need. And the post and points left as a legacy when we migrated from REST, so we didn't change them.
Okay. I also wanted to add what's related to ProSoft. When you talk about that you can create a different application without the need of the backend. So also, I think for the development, it's very relevant as well because it allows separation of client design and backend design, because client designers, we can experiment during development and we do not need to go to backenders and to ask to do something. Is that right?
This is absolutely right. I would even say more. So modern applications usually developed with a user experience in mind, so-called UX. And sometimes when UX gathers metric, they realize that, well, people do not click this button to use this stuff. They use a slightly different thing. And technically, this is not a really functional change from the application standpoint, but UI has to be redone. And in this case, GraphQL really works well, because if now some of the components need to request an additional field, you do not need to create an additional endpoint or even make your logic more complicated. You need to include this field in a query, and you will get it in the same place as it was previously. So this indeed allows a very good separation of what is happening in a front-end development from a backend. So technically speaking, if you really support GraphQL on the backend, the only reason for front-end guys to come to you and say, hey, change your API, is when they need new data. So actually, this is an extension of your domain. You need to provide something completely new. And this is usually a common extension of domain, like feature development. We develop a completely new feature with new data, then we extend the API. So it's very natural.